Hello, on behalf of Task International, welcome. My name is Peter Rittmeyer. In this training we are going to give an overview of the MBNB contacts. The next topics will be addressed. We will discuss the several forces and boundaries, penetrations. Probably too much detail at this moment, but let's go through it step by step. Well, choosing an MBNB algorithm is pretty straightforward, as there is only one type of contact available. It's a force-based contact of the type characteristic. Forced means force penetration, so independent on the area, the contact area. Here you see an example of an MBNB contact. In red there is a master service, in blue there is a slave service. As you can see, the forces are built up from an elastic, a damping and a friction. And the friction force is always perpendicular to the elastic and damping force. In this case it's penetrating because the elastic and the damping force are pointing in the same direction. Once the master surface, or let's say the contact, is moving outwards, the damping will be changed in direction, as it is always resistive. You have to define group MBs. In this case there are only just two, a master surface containing one ellipsoid and a slave surface also containing one ellipsoid. However, it's possible to define multiple ellipsoids in one group E, so for the master as well as for the slave surface. In this case, as you can see in the example, is the contact type mentioned slave. It means that the slave is the deformable and the master will remain rigid, so undeformable. You will see later on that there are other flavors available as well. Elastic force. Let's focus on that first. You see the contact characteristic at the left side and the curve is presented at the right side. There's a loading function and an unloading, which are connected by a hysteresis slope. The damping is pointing in the same direction as the elastic, but as said, if it's moving outwards, so a decreasing penetration, the damping force will change direction. Take this into account, because the damping force can never be higher than the elastic one. You have to define the damping characteristic yourself, unless you make use of the dummy characteristics. The damping force is built up from several components. You have a constant damping. You can even define your own function, which is dependent on the velocity. On top of that, you can link it to the elastic force. Now let's focus on the friction force. This requires a little bit more explanation, because as you can see in the example, you can define the friction in two locations. Under the contact MBNB itself, it's the friction coefficient. That's probably the most common one. In the friction function, you'll see there's a little remark made, because you might expect that it is relative with respect to relative velocity. However, for the MBNB contact, that's not, because it's relative to the normal force. You see an equation under the friction force, which I will explain now in more detail. We will go from the right to the left. The Fe and the Fd, so the elastic and the F damping force, that's the sum. Then the function left from it, that's the friction coefficient. That's the sum of the friction coefficient defined under the MBNB contact, as well as from the friction func. Then C requires probably the most explanation. It's introduced to prevent numerical noise if the velocity, the relative velocity in the contact, so between the master and the slave surface, is low. Basically what it says, if it is below 0.01 meters a second, there will be no friction force applied. It's considered as being standing still, but you're not able to define any stiff slick. Then gradually from RACO 1 to RACO 2, the value C is increased to 1. If the velocity is higher than 1/10 meters a second, it gets the full frictional force. Now let's focus on what is a penetration. How is it calculated? How is it derived? In this case, you see a plane and an ellipsoid. Bear in mind that the planes do have a normal. If it's pointing outward, that means there is no contact. Ellipsoids and cylinders have it automatically correct. It's always pointing outwards. But it might be that you have set up your plane in a wrong direction, and due to that, maybe the whole ellipsoid is already inside. XMagick and MAPOST provide tools to check those things. Well, let's focus now how is the penetration derived. You have the plane, and in the same direction you will derive the tangent of the ellipsoid, and that is called the penetration. Something similar is occurring of an ellipsoid to ellipsoid contact. Again, you derive the tangent of both ellipsoid 1 and ellipsoid 2. Perpendicular to both tangents, that is called the minimum penetration, and that will be used to derive the force related to the penetration, which is defined in the contact characteristic. Something similar is occurring for the cylinder-ellipsoid contact, as you can see here. Boundaries of planes. Let's assume you have a plane ellipsoid contact. In this case, in the picture you see that the ellipsoid is moving to the left in such a way that the penetration is outside the plane. You might imagine that if this is happening in one time step and the contact force is high, you will have a tremendous drop in contact force, because if it's outside the plane itself, the contact force will be 0. Well, boundary width gives you the possibility to control this in a better way. By default it's 0, meaning if the contact point is outside the plane, it will be 0. You can define a positive value yourself. You can also put it to inf, meaning infinite. It means that although you see the plane as defined, in reality for the contact, for this specific contact, because the plane can be used also for other contacts as well, but for this in this case, the plane is considered as infinite, and therefore you will never have the possibility that it gets out of the plane itself. Here you see how it's working in more detail. The point A, B, C, D are the endpoints of the plane itself. Well, the width, that's the boundary width. And here you see it from the side. If it's inside, but not more than the width length, you get the full force. But then gradually it's reduced, the contact force, if it's moving outward the plane. If it's on the edge of the plane, the contact force is already reduced to 0.5 of its defined value. And if it's one width outside the plane, the contact will be 0. You can imagine that this makes the contact more robust, less sensitive for noise, but maybe you don't like it to be like this, so it's a user-defined parameter. Let's go to the contact specification. You have a master surface, and that's a group of ellipsoids, planes and cylinders, and that's called the penetrated surfaces. The dummies, for example, have already predefined group MBs for that. If you make your own models, you have to define your own group for that. The slave surface is considered as the penetrating. Those can only be ellipsoids. One of the first slides I mentioned that the contact type was slave, meaning that the slave was deformable. Well, there are other flavors available as well. You can define a master or a user master. User master means that you have defined your own characteristic. And that means that the master is deformable. In this case, you see the master plane and an ellipsoid slave, and the point where the contact force is applied is on the slave surface, because the master is considered to be deformable. For slave, it's just the opposite. Well, there are other flavors available, which you see on the next slide. You can define a user midpoint, which means that the master and the slave are considered to deform more or less equal, and then halfway the deformation, or the penetration maybe that's better said, that's where the contact force is applied. There's even another option which is combined, and then the contact characteristics of both master and slave are taken into account, which means that they also consider deforming both. Initial penetrations. It might be that you have positioned your dummy in such a way that the contact forces are too high, and for that is not standing in equilibrium. Well, obvious, you need to check whether your model is such as it should be, because it might be that you have positioned the plane or the dummy at the wrong side. But if, for example, if the contact characteristics are very stiff, it might be a very sensitive way to get equilibrium. Well, this might then be an option to use initial type correct. What is it doing? Initial type correct means that if there are initial penetrations, the forces are set to 0. Be aware that this might also disturb your equilibrium. For that reason, it's generally recommended to use initial type none, which means if you have initial penetrations, contact forces will be applied. Now let's move on to the last slide. That might be a bit of a complex one. Evaluation. It can be non-discrete or continuous. Let me first say that our dummies are designed or evaluated with the type none. What does it mean? Well, let's suppose the pictures you see is a pelvis sitting in a seat. Each ellipsoid penetrating the plane will get its own independent local force. That's the way, as said, the dummies are designed. However, if you put it too discrete, then only the ellipsoid which is producing the maximum elastic force, only at that ellipsoid a contact force will be applied. You can imagine that if the ellipsoids of the pelvis are rotating around the x-axis, you get something like a discontinuity, because at a certain moment maybe the left ellipsoid is penetrating more than the middle one. For that reason, this one is also not recommended to use. Ideally, you should use the evaluation type none. There's the third one, which is continuous. It's preferred above discrete. What is it doing? Just like in discrete, it will derive the maximum elastic force. But then based on the individual penetrations of each ellipsoid, the contact force is distributed over the contacted ellipsoids, which makes it more smooth. That brings me to the end of the MBNB contact. Goodbye.